Stuck on CNA labs? Tired of scattered tutorials? This full course covers every exam topic with real lab configs. Grab your free lab in the description. Ready to pass CNA and boost your career? Start now!
Hello everyone. In this lesson we'll learn about ping and traceroute. These two tools, both ping and traceroute, work based on the ICMP protocol, especially the ping utility. Ping and traceroute are both used when we troubleshoot. Two tools we use very often, mainly to check two things. Ping is mainly used to check network connectivity. Whether it's reachable, you can use ping for a quick check. Traceroute is used when we troubleshoot the path. For example, between PC1 and PC2. You first try to ping and find that PC2 is unreachable. Exactly where is the break? At this point we can use traceroute. It will trace our path and show where along the path it breaks. It can display that. This way, you can focus on that specific device to find out why it's unreachable from there. Right? So ping and traceroute are two very useful tools. A network engineer should master them proficiently, because you'll use them heavily in daily work. Let's first look at the ping command. The ping command is actually very simple. It's just ping, followed by the target host we want to reach. That is, the packet sent to which host. After the remote host receives our ping packet, it needs to send back a reply to tell me if it arrived. Right? In other words, it needs a read-receipt of sorts. At this point, here we need to fill in the remote device we want to access. For example, we access R1's interface 0/0, which is 192.168.10.254. We can verify that this is the address. Then we can ping it. If it goes through, then that means it's reachable. On our Cisco device, an exclamation mark is shown when pinging, and this means the destination address is reachable. The destination address is reachable. This is very simple. Right? When pinging, the source IP is the IP of your own, the destination IP is the peer's IP. The peer's IP. So this command has some derivative usages. For example, by default, our Cisco device, when pinging in a unicast network, sends 5 packets by default. It sends 5 packets at a time. It pings the peer with 5 packets. Then the peer replies with 5 packets. So 5 exclamation marks are shown here. Right. If you think this is too many packets, or too few, and you want to specify the number of packets to send, right? For example, if you want, then use repeat. Repeat means repetition. Right? After it, write the number of packets we want to repeat. For example, we only want to send 1. Right? Then it sends 1 packet. 1 exclamation mark. 1 right? If you want to send 100, it's also just send 100, right? This is very fast. Because the time, right, is shown here. What is the success rate? Right? It's 100% here. 100 packets, and 100 along the entire path. These packets. Out of these 100, what is the minimum delay? From me sending to, and the other side, how long is the delay in between? Right? So the smallest packet took 1 millisecond. Let's look at the top one. The smallest packet took 1 millisecond. The largest packet took 1008 milliseconds. Right? And the average is 202 milliseconds. 202 milliseconds. Usually, this is the first packet. When you ping a host you've never pinged before, its first might take a bit longer. Or even, the first packet, this is quite normal. Because at this, it hasn't obtained the MAC address yet. It will perform an ARP, only then can it get it. Right? After getting it, it can encapsulate. Then the packet is, this process takes longer. This one might time out. After the timeout, the subsequent packets are fine. Right? So for the first, this packet loss, or long delay, is very normal. Then afterward, basically speaking, this time will be, especially for direct network connections like this, it's generally 1 millisecond. This specifies the number of packets to send. This is the number of packets. So, besides specifying the number of packets to send, it also has some other useful tools. For example, the size. Generally speaking, our ping packets are actually very small. Sometimes we need to test some large packets to see if they can be sent through. In this case, we can specify its size. The size of this packet. Right? For example, the minimum is just 36. Right? And the maximum is this large. Right? So you specify a packet of this maximum size and send it over. Right? That also works, but you will find its time becomes longer. The time becomes because the number of your packets. The size of this packet is too large. If it's too large, as we mentioned in the old OSI 7-layer model, when your packet size is too large, it needs to be fragmented and segmented, right? Right? It needs to be after fragment, the other side will right? Therefore, in this context, such a large packet actually, on the device, it first splits it into several pieces and sends them, then the other side has to reassemble them. Only after reassembly does it respond to you. Right? We can capture packets here to show you. Wait for the packet capture software to start. There are no packets right. Let's search for ICMP packets. We can just look at ICMP. Then let's ping again. What follows is the ICMP packet. Right? Then you can see below. This data, right? Such a long string. Then let me pull it up. Look, there is so much, right? If we do not specify the size. Let's see what the size is. Look, you can see its data is this much. Right? Length. So if not specified, let's scroll down to the latest one. Look, isn't this only 72 bytes at the bottom? Right? Only 72 bytes. What follows is all ABCD, right? All ABCD, filled with just a small segment, but for the previous one. Look, it has such a long, right? This entire string is all ABCD. ABC, a very large amount. This specifies the size of our packet. Specifies the packet size. Oversized packets may fail to send. This depends on the interface settings on both sides. The interface settings on both sides. Generally, such direct connection issues are not a big deal. So, this value is rarely used. Only when testing specific applications. Will we use it? To specify the packet size. In addition to specifying the packet size, you can also specify the fields in the data portion. Like here, the default is ABCD. If you don't want it to send ABCD, you want to specify something of your own. That is also but it requires encoding in hexadecimal. Encoded in hexadecimal. You use ABCD. Right? Let's look at the final result. Right? Actually, ABCD is not obvious. Let's change it. FEDC. Right? Send it like this. You can see the padding is now FEDC, right? Right? These are the padded fields. The padded fields. If you don't write anything, it defaults to ABCD. It defaults to ABCD. Then you specify, and it becomes the value, right? Specify what this value, you have so it will be used, right? But you can only enter only 4 characters. Entering 4 zeros, right? 000. Let's send it again. Check the bottom. The header is followed by all, right? This specifies its data. This is the data part of the sent ICMP packet. Don't worry about this df bit. This is a bit early for everyone. This is quite difficult. Then the src command. This one is also, it is indeed used quite often. Normally, when we ping a target. For example, when PC1 pings the remote interface. By default, the destination IP address is the target you specified in the ping. Right? As for the source IP, by default, it is the outgoing interface of this packet. The outgoing interface, say interface 1020, right? The IP address inside it. However, sometimes, for instance, when R1 needs to ping PC2, I do not want to use its outgoing interface. By default, when R1 pings PC2, its default outgoing interface should be this 0/1 interface, right? Because the route goes in this direction. Right? But sometimes, I want to use its loopback interface. Or, use its lower interface 10/0. as its source IP address. When the time PC2 will send the reply packet back to my 10/0 interface to the 192.168.10.0 network segment. I can test on behalf of PC2. To test this. On behalf of PC1, right? To test the connectivity with PC1. You can test this. If you do not specify the source. For example, in our current, we configure a static route. To enable connectivity between PC1 and PC2, right? Let's configure it quickly. We covered this in the static routing section earlier. Right? We'll cover that later. If you haven't learned it before, we will cover it later. Don't worry about it. Anyway, you need routes for connectivity, right? This side is 20.0. Oh, the configuration is done. Now let's ping PC2 from PC1. Ping 20.1. PC2 should have the IP 20. Let's verify. Yes, that's correct. So let's ping PC2 from PC1. It's reachable, right? Okay, now, if I user 1 to ping 192.168.20.1, meaning R1 pings PC2, you will find it fails. It is unreachable. Here, we can also take a look. See what a failed result looks like. Right? So, is shown as a dot. As an indicator. Of course, it's not just a dot. It's not only shown as a dot. There are other indicators too. For example, a U. When a U appears, that also means it's unreachable. Besides the exclamation, all other symbols. Not just the dot, right? This U, sometimes it's an M, right? There are many symbols. Only the exclamation mark means success. All other symbols indicate errors. Various types of errors. Okay, so this is a failure, right? Why does it fail? When R1 sends a packet to PC2, its original destination IP address is wrong. Let's capture packets on R2, for example. I'll show what is its source IP address? Wrong interface. Interface 0/1, right? Open another one. It's the same, just use show ICMP. Then have R1 send the packet again. Hey. Now you can see it. Notice its source IP is 12.1.1.1, right? That is the IP address of R1's interface 0/1. For R3, it does not have an IP address on the 12.0.0.0 network. It has no route for it. Therefore, when these packets reach R3, it cannot send a reply. It cannot return, so it can go out, but cannot come back. So, it's unreachable. In this case, here on R1, I can specify its source IP address. Set its source IP to the IP of interface E0/0. Okay, let's change it. On R1 here, make its source IP address the E0/0 interface. Of course, you can also directly type, the IP address is 192.168.10.254. Right? Both methods work, they are the same. Oh, now it's reachable. Let's check its packet capture. Right? Just now, 12.1.1.1 was the source IP address. That's why it was, right? So the second time I ping it, you'll notice that its source IP address becomes 10.254. So the 192.168.10.0 network segment. That's the network segment where the PC is located. Right, so this one can get through. So when we do some troubleshooting, when doing fault diagnosis, you need to pay attention. The object you're testing. Source and destination. Right? Who exactly are the source and destination? When I send the packet, its source IP address and destination, you need to verify them. You can't just directly ping like, that would certainly be different. But actually, both of these routes are fine. Both can get through, right? It doesn't mean it, so when testing, you must pay attention to what its source IP address is. If it's the egress then you don't need to specify, right? But if it's not the source, not this egress, then you need to specify who the source is. What the source IP address, You need to modify its source IP only will the test be meaningful. At the NA level, this phenomenon might be relevant, but in real work at the NP or IE level, this kind situation where the source is not its outbound interface is quite common. It is quite common. So everyone should pay attention to this. This is the specified source. Specified source. Okay. And then, there is which is timeout. By default. The ICMP packet. I send it out, and the other side sends it back to me. The timeout value in the middle is 2 seconds. As long as you reply within 2 seconds. That is acceptable. That is acceptable. If you exceed 2 seconds and still haven't, then I consider this packet. The destination is unreachable. Meaning it is unreachable. This timeout value defaults to 2000. If you think this time is too long, right? You can change it yourself. However you can change it yourself. It's 0 to 3600. 3600 is 1 hour, right? The default is 2 seconds. You can change it yourself. For example, we set it to Actually, it's hard to test here. Because the delay time is just milliseconds. Right, just milliseconds. This is very hard to test. But we can see here. The timeout is 2 seconds, right? Let's change it to 10 seconds. This is unreachable. You can see the timeout is 10 seconds. Right, okay. Sometimes when we ping, it doesn't show up, right? It doesn't, or say I ping 5 packets here. And the first packet gets stuck. Then the second packet doesn't. I want to interrupt this connection. Interrupt this ping. Stop this ping. How do we stop it? Pay attention. Press Ctrl+6. Note that only Ctrl+6 can interrupt it. Commands like Ctrl+C won't work. It must be Ctrl+6. Ctrl+6, got it? We set the language, right? The language is interface 1/0. Then it can connect, its timeout is this. The timeout is this. Then the source IP address is this target. The destination IP address is this, right? This shows very clearly. The others are rarely used. So regarding ICMP, we have covered these ping commands. The most used one is specifying the source. And then repeat to specify the ping count. These two are used more often. Of course, when pinging, there are actually some other parameters available. Other parameters can also be used. But our current iOS has relatively few command functions. Only these few, right? Some more powerful iOS versions have other commands. We'll cover those later if we get the chance. So that's the ping command. Next, let's talk about Traceroute. Traceroute. Let's first see the result. Traceroute 192.168.20.1. Okay, you can see here. The first hop is 192.168.10.254. And here are the 3 packet times. Right? Then the second hop is 12.1.1.2. Then the third hop is 23.1.3. The fourth hop is 192.168.20.1. So what are these 3 or 4 things? After PC1 sends the packet, which devices do these packets pass through? The devices they pass through. Or what are the IP addresses of, right? After leaving my PC, it reaches this interface on RE, correct? The IP address of this interface is 192.168.10.254. That is its first hop. Its first hop, right? Then after reaching this RE forwards it to the second device. The second, it enters through the G0/1 interface of R2. And the IP address, it is 12.1.2, right? Then it goes to R3, right? This interface is 23.1.3. Then it reaches PC2. The G0, it enters and reaches 20.1. This is used to trace its path. Used to trace its path. Which devices do our packets pass through along the way? Right? Which devices do they pass through along the way? Now, suppose we have a problem on a device in the middle. A certain problem occurs. For example, I shut down the G0/1 interface on R3 here. This interface here is shut down. Right? Okay, now let's see the effect. See that? The first hop goes to this RE. Then to R3. Then we find that at R3 here. It is unreachable. Right? It stops showing. It gets stuck here. So in this, when we trace the path, we can discover the problem occurs at our, so the problem must be at R3. Then you can go to R3 to check it. Right, what exactly is going on with, right, we can take the fault and pinpoint it to a specific device. Pinpoint it to a specific device. These are the two more commonly used tools. Of course, Traceroute also has some advanced usage. For instance, with Traceroute, it also has some common tools, such as this. No metric. No metric, what is this? By default, our device has this DNS resolution feature, but we have it turned off by default. Right, we enable its DNS resolution feature. IP domain. Look up, enable it, then we run Traceroute again. You'll find the speed of this Traceroute is nowhere near what it was before. Right. Or if we shut down, right. You'll find the speed is very, very slow. Right. What is it doing? When it performs detection. Each hop tries to do a DNS resolution to find the current IP addresses. Domain name. Domain name. For example, let me show you. The real host, right. Our computer also has Traceroute, right. For example, baidu.com. There's packet loss in the middle here. This is probably due to some ISP policy restrictions. The policy blocked it. It doesn't display. Every hop tries to perform DNS resolution. So it takes a longer time. It doesn't display here either. If it doesn't display, forget it. Sometimes we can see its domain name. This is time consuming. Some might say, I'll just turn off its demilookup. That works too, right? Like we did no IP demilookup. Then the resolution speed is very fast, right? The translate speed is very fast. But some devices we don't allow no IP demilookup. For example, this device is the gateway. And it also serves as a DNS relay service. Right? For these, you cannot disable their demilookup. What do we do then? You can follow the translate with a non-metric parameter. It won't try to resolve its DNS domain name anymore. It won't try to resolve it anymore. This can be useful sometimes. Can be useful. The second one is port. Translate can specify a certain port number. This is rarely used. Generally, we just test if an IP is reachable. As for port reachability, if the IP is reachable, the port may not be, right? You can use Telnet to check if the port is open. As for using Translate, generally we don't test its port number. Then, third. The third is the probe. By default, the probe. We can see that it detects 1. For detecting, it sends 3 times. It sends 3 times. We just captured packets, right? Look, let's capture again. Capture again. Oops. It scrolled away. Let's capture on R2's interface. Interface 0/0. Then we use Traceroute. For example, when accessing a target. 192.168.10.1 is the return packet. Right? This is the return packet. You'll see it has 3 packets, right? Same here above. From 10.1 to 20.1, right? From 10.1 to 20.1. It sent 3 packets in total. It sent 3 packets over in total. Same below, right? Also 3 packets. So by default. You can also see here. The 3 timestamps are displayed. By default, Traceroute sends 3 probes. 3 probes, meaning it sends 3 times. To detect the path to the target, right? If you think 3 times is too many or too few, you can specify the number of probes after it, right? 1 or over 60,000, right? For example, let's send 5. Then it shows 5 below, right? Look, all the timings are displayed now. Right? Say you want to test 100, right? That works too. Then all the timings will be pulled out for you. All pulled out for you. This sets the number of probes. The number of probes. To end, use show control plus the 6. Now let's check if there are other common ones. Source. The source refers to when you send this traceroute packet. What is its source IP address? It works the same as the ping command. It works the same, for example, when we use or when using Traceroute, right? You can specify its source. It can be its E0/0 interface or a loopback interface. Or any other interface. Okay? I won't demo this one. We just demonstrate. Timeout is the same as the previous one. Now TTL. TTL sets its minimum and maximum values. Here I need to explain the principle of Traceroute. Regarding Traceroute's principle, we need to capture packets on this 0/0 interface. Didn't we just have a packet? Let's capture again. We'll capture from PCE's 00 interface. We'll send a single probe. This makes it easier to observe. Easier to observe its behavior. Other principle. Send a packet. Wait a moment. Let's add this one too. Okay. This is what was just sent. Sent from 192.168.10.1 to 20.1. Right? Inside this, you'll find in its ICMP packet. There's a field called time to live. This is the so-called TTL. Its value is 1. We all know when TTL equals 0. This packet will be dropped, right? Okay. So at this, the first packet PCE sends has a TTL value of 1. When the other end, R1, receives it, it reduces the TTL by 1. It finds it equal. This packet is then, after being dropped, our R1 will reply to. It will reply. It replies to this PCE, right? So this is our R1. The reply is from 10.254 to 10.1, right? The TTL expires, right? Their TTL is insufficient. So it sends back this packet, right? It tells you the TTL has timed out. Then it sends back a message telling you it's not At this point, I know who my first hop is. Is it you who replied to me? So the first hop is 10.254. Now I want to check the next device beyond it. Who is the second forwarding device? Now pay attention to what follows. When the packet is sent a second time, see? TTL equals 2. When this packet reaches PCE. After it reaches R1. TTL decreases by 1, making it 1, right? R equal, then it can forward the packet normally. Forward it, right? After forwarding to R2. R2 sees the TTL is 1, right? I need to decrement it by 1, so it becomes 0. It's discarded. After being discarded, a packet is sent back to our PCE. Then it returns to our PCE. At this point, my PCE receives a TTL timeout message. A time exceeded packet returns from 12.1.2. This is a TTL timeout message. So I know the second hop. The first hop is 10.2, the second hop is 12.1.2. By this logic, for the next packet, I set its TTL to 3. Can I then discover the third hop? Who is the second hop device? Right, and when TTL equals 4, it reaches the destination. Right? It reaches the then the destination replies to me. The TTL times out, right? The target is reached. This is what we call the principle of traceroute. The principle of traceroute. The principle is, when testing a certain path, the first traceroute packet sent has a TTL of 1. So in this, the first hop, upon, will reply with a time exceeded message. This way, from its source IP address, the source IP address of the returned packet, we can determine who my first hop device is. Then, set the TTL to 2. So we can skip the first device and directly probe the second device. Right, then the second device, so I know the IP address of that interface. This is how it detects. detects the path. That's the principle. The principle of the traceroute tool. Okay, so for ping and traceroute, we'll stop here for now. As for these two, we will use them frequently during testing and troubleshooting. Will be used frequently. You'll gradually master them later on.